I will put the link in. I will put the link in Blackboard after the lecture.
Yeah.
Put the link. So as you can see here in this example, I can in this example it's just to revise what has been done last time. So we can use this perceptron for any binary classification problem. So if you have multiple inputs x1, x2, x3, x4, whatever, it's connected with this node with weights omega 1, omega 2, and omega 3. For example, we have the bias. The input to the bias it's +1. We need to adjust. We will calculate net value. So this net value, it will be, we will calculate net. So this net, it will be omega x summation of omega x plus p, right? I equal 1 to n omega I multiplied by xi, for example. So this one will be our decision line. And after that, you need to adjust weights. So you will use this equation delta omega equal eta multiplied by error multiplied by input. Delta b, it will be eta multiplied by error multiplied by the error, which is multiplied by the input, which is +1. And the error will be my target minus y, minus prediction. So it will be like this one. So sometimes this error will be positive, sometimes will be negative. And based on this, we will be able to adjust our weights. So this is the perceptron, and we can use this perceptron for binary classification problems. If you want to use binary classification, maybe you will select the threshold or activation function, this one step function, or symmetric activation function, for example. If you want to use it for regression, in this case, we need to use linear function. So we will use this one. We will use this function. So it's very easy to use it. So now we need to use gradient descent. If we need to expand this model, okay. So if you want to expand multi-layer perceptron, it's just number of layers. So if we need to make it larger, we can just say, okay, we will have maybe one hidden layer, maybe another hidden layer, correct? Output layer, correct? Something like this one. So now it will be, we have here input layer. So in this case, our model will be more complex because we call it MLP, multi-layer perceptron, multi-layer perceptron. So in this case, we cannot use, when it is multi-layer perceptron, we cannot use perceptron learning rule. This one, we call it BL, or perceptron learning rule. We cannot use this one, and we need to use some other technique, which is a gradient descent. So gradient descent, it's first order iterative optimization algorithm for finding local minimum of a differentiable function. So we need first to define a loss function, and this loss function should be differentiable because we will take the first derivative to minimize this function. So it's very important when you are selecting a loss function to select a function which is differentiable. The idea is to take repeated steps in the opposite direction of the gradient because it's a gradient descent, not ascent. When it is gradient descent, in this case, we need to move against, we need to move in the opposite direction of the gradient because we need to minimize. If you want to maximize, you will move with the direction of the gradient of the function at the current point because this is the direction of steepest descent. We will use iterative gradient descent, which is called the stochastic, and the stochastic gradient descent, they call it online gradient descent. Why? Because we try to update the weights for each single input or each single example. So if your data set consists of 100 points, we will do this stochastic gradient descent where we will adjust the weights for each input. We call it online. So when you have any data points coming in, you can just adjust your weights. First, we need to calculate a loss function, or we need to define a loss or objective function. This loss function, it should be summation of it should be a summation of a function square. It could be error square, for example, because we need to have it. Yeah, it will come. Yeah. So this function, it is a loss value which is associated with ice, maybe observation or example. And once we calculated this loss, once we have this function, we will update the weights. Those weights will be omega equal omega minus eta. This one should be negative, multiplied by the gradient of this loss function. This one, it's the gradient of this function with respect to omega. So this is our, so we need to calculate delta omega. So delta omega will be minus eta multiplied by the gradient of this loss function, for example, right? For omega, so it will be the minus eta, which is the learning rate multiplied by the gradient. And we can do it, in fact, for each example, or we can do it, in fact, for a batch of examples. So it could be done for each single example. In this case, we will call it a stochastic gradient descent. And you can do it for a number of examples. And in this case, we can call it batch gradient. This batch, the size of the batch, it could be the whole data set. And in this case, we will call it batch gradient. And you can do it for many batches. So it's according to your memory needs. Maybe you can do it for a small batch of data, because you can divide your data set into maybe number of batches, where each batch has a number of examples. So we can call it mini batch gradient. So it could be batch gradient, and it could be mini batch gradient, and it could be stochastic. When it is a stochastic, we call it online. So we will adjust the weights for each single input, or each single example or observation, for example. When it is batch gradient, in this case, we need to define the batch size. So if the batch size will be n examples, so in this case, we need to take the average. We need to calculate the average of the gradient over the batch, and we will use this value for adjusting the weights. So if your data set consists of 1,000 points, and if you will go for stochastic gradient descent, you need to adjust, you need to do those calculations 1,000 times. But if you will divide your data set into, maybe imagine 2 batches, and each batch will consist of 500 data points. So in this case, we will calculate the average gradient over each batch, mini batch, and we will adjust the weight only one time for that batch. So in this case, in each iteration, if we will train the model for number of iterations, in this case, we will train the model here, we will adjust the weights only 2 times each iteration. If you will divide your 1,000 data points into 2 batches. So in this case, you will adjust your weights 2 times each iteration or each epoch. But in case of stochastic gradient descent, in each iteration, you need to use the whole 1,000 data points for adjusting the weights. So you will do those calculations 1,000 times. So in fact, it's maybe computationally intensive when you go for stochastic gradient descent, but when you go for batch gradient or mini batch gradient, number of calculations will be much less. But of course, you need to have maybe larger memory for holding or storing all the batch size or your batch of data points. So the intuition behind the gradient descent, it can be just imagine that it's this hypothetical scenario. You have a person, and this person is stuck in a mountain, for example, and it's foggy. You see, it's foggy around him, and he tried to go down. So he tried to search for the global minimum. So in this case, there is no visibility. You can see very little because of heavy fog, for example. So the visibility is extremely low. So he tried to just use a path, find a path where he can go down the mountain by using local information to find the minimum. So he will just look around, and he tried to find a path, for example, which will lead him to go down the mountain. So they can use a method for gradient descent, which involve looking at the steepest steepness of the hill, for example, at this current position, and he will proceed in the direction with the steepest descent downhill, to go downhill. If they were trying to find the top of the mountain, for example, he will do the opposite. He will search for the maximum. He will go with the direction of the steepest ascent, not descent. So you need to decide if you want to go downhill or uphill. Using this method, they can find their way down the mountain, or maybe they will get stuck in some hole, for example, which is local minima. So for example, maybe you have this example here. This is your cost function, and this cost function, if it is convex, in fact, we square this function to be convex. So if your function is like this one, we will be very lucky, because we can start from any point. We can start from this point, try to go into that direction, and we will reach this location. If you are starting from that direction, it will be the same. We need to go into that direction. And we use here the gradient, which is the slope of this line, for example. And you will just keep going down until this slope equals 0. When it's 0, it means you will stay here because you will not be able to move any further. If your function is non-convex, we have here a risk, in fact. If you are starting from this point, maybe in this case you will stuck here in this local minima. We call this one local minima. So if you are starting from here also, maybe chances that you will stuck here, it will be very high. You will be here. Maybe we will be very lucky because you will start from here. So in this case, you will go to this global minimum. If you are here also, we will be very lucky because you will go directly into this global minimum. So we have chances. I mean, there is no guarantee when we are using this gradient descent approach. There is no guarantee that you will be able to get the minimum. But to avoid this problem, you just need to run your algorithm maybe several times, because when we try to adjust the weights of a feed-forward neural network, imagine that it looks like this one. We have an input layer which has 2 inputs. We have a hidden layer which has 3 neurons, for example, and we have an output layer which has 1. So it will be like this one. My perceptron, my multi-layer perceptron, it will look like this one. So in this case, we need to adjust the weights which are connected to each layer. We have here weights, I will call it V1, for example, V2, V3. We have here some weights, omega 1, 1, omega 1, 2, omega 2, and so on. So we have those weights we need to adjust. If your function is non-convex, if your error function is non-convex, so you don't know if we will be able to reach this point. So to solve this problem, you need to train your model several times, and each time you will start from different random set, because when we train our model, we initialize the weights with random values. So the idea here, don't start from the same random values. Don't use random seed, because if you will use a random seed in front of your code, what will happen each time we will generate the same random set points or set values. So you will start from the same point. So to avoid this problem, don't use random seed, and try to train your model from different locations each time. Maybe sometimes we will start from here. Maybe sometime we will start from here. If you are starting from here, you will reach this accuracy. Maybe this accuracy here will be maybe 85%. If you are starting from here, maybe you will reach an accuracy which is 98%. If you will get 85% and 98%, you will understand that you have local minimum, right? And you have global minimum. So in this case, you will know surely that you need to reach this global minimum and not that part. There is no way to see the cost function or the loss function, but the best way for solving it to just start each time from different initial random weights, different random set or random weights. So just repeat the training process several times. If each time you are getting the same accuracy, it means your function is convex, right? If you are getting different values each time, in this case, it means that our function is non-convex, and we need to start from different random values in order to be sure that you are able to reach this global minimum. So to get the gradient of the cost function, you need to derive its first derivative. It's very important to get the first derivative of your function. The loss function, you need to square it. So in this case, when we square the function, it will be convex, right? We need to have a convex function in order to be able to minimize it. So we can just take an example. You have this function, 5x squared plus 2x minus 4. So we need to find the gradient. This one, it's not this one. It should be like this one. This is the gradient, in fact. We need to get the gradient with respect to x. So the gradient would be the first derivative of this function. So it will be 2 times 5, it will be 10x, plus 2 times x, it will be 2. So this is my function. When you plot this function, I mean, this is f of x, in fact. This is f of x, and the function is convex. So we need to minimize. So we need to find x, which will minimize f of x. We need to reach x star. So we need to reach this point. And the function at that point, in fact, it's 0, as you can see here. So x here, I mean, if you need to minimize f of x, we need to minimize f of x, right? So what will be the value which will minimize? I mean, it will be x star. So we need to find this x star. So if you want to solve this problem analytically, you can just, in fact, you can just I mean, if you want to solve it using gradient descent, so just you need to find the gradient. It will be the first derivative of this function. It will be 10x plus 2. and after that we will need to update. We need to adjust x or update value of x. So x will be x plus delta x. What will be the value of delta x? Delta x will be this value. So, but you need to start from some initial points. So assume that we are starting from x equal minus 10 by random. We selected this point by random, right? So in this case, x equal minus 10. We are starting from this point. So we will calculate delta x. So what will be delta x? So delta x will be, yes, please, Sophia.
Yeah. Yeah. So
Reproducibility. Yeah, sorry,
yeah,
I
yeah.
read. Yes, this is correct. I mean, if you want to reproducibility, you need to do this when you are sure that you are able to minimize or optimize your model, right?
Yeah, for example, if you want to rerun it again at some point in
Mhm.
time for scoring or for production point from production point of view, then how would we share reproducibility? And if we use the seed, then you can compromise your performance. So, what is the trade-off here? I mean, I just want to know about that.
Yeah, it's a good question because maybe by chance, if I didn't use this, if I use the random seed, for example, so
Mm-hmm.
I will train my model, and by chance I got accuracy 95%, right?
Hmm. Yeah.
And then now you said, okay, you wrote your paper and you send it, you put it in GitHub, so people
Mm.
started to download your model and use it. But maybe
Yeah.
someone else he try to reproduce your results, and he will
Hmm.
train his model, and he got accuracy of maybe 75%.
Hmm.
So it will be very bad, right?
Yeah.
So because it's just by chance, because you trained your model and by chance you got this nice accuracy, and he will run his model, and he was not lucky, so he will got this kind of accuracy, which means our loss function is non-convex. So
Hmm.
so first we need to ensure that we need to see how this loss function looks. Is it convex or is it non-convex? So how can we do this? We need to run my model several times, and we don't need to use this random seed. So I can explore the shape of the loss function.
Hmm.
If you will train your model 10 times, and each time if you will get the same accuracy, it means your loss function is convex. So now you are safe. You can just train your model one time and you will be safe because your loss function is convex. But if each time you will get different accuracy, so in this case
Hmm.
maybe I need to in this case maybe I have my model. I will train my model, for example, for 10 times, and each time I will get different accuracy. So in this case, I will say that okay, I will take the mean and the standard deviation. So I will say that okay, the accuracy of my model is this mean value plus minus standard deviation.
Hmm.
You will say that I will train my model 10 times, and each time you are getting a different accuracy. So at the end, you will just say that okay, my model will have a mean accuracy plus minus a standard deviation. So instead of giving exact value, which is 95%, no, you will say no, it's not 95%. It's 75% plus minus 10%, for example. So people now,
Hmm.
when they read your results, they will say, okay, well, we should expect that we will be, we will get an accuracy from maybe 65 to 85%. We will have a range. It will not be an
Hmm.
exact value, right?
Hmm.
In
Yeah.
this
Yeah.
case, if someone will train your model one time, maybe he will get 65%. It will be correct according to your results. If he got
Hmm.
70%, it will be correct. If he got 85%, it will be correct. So now
Hmm.
you will be safe because you provided a range,
Hmm.
right?
Yeah. So is it possible that, for example, if I train my model 10 times and 20 times, and
Hmm.
now I know the range of my model that is quite reasonable, and it's not by chance, it's really a convex function. And then after that, I can fix my seed for from reproducibility point of view.
But if you fix it your seed, you will get one results, right?
Yeah. I
You
mean,
will
from
get only you can do it like this, of course, but your model will have this the accuracy of your model will be a range. It will not be an exact value. It will be a mean value plus minus standard deviation, right?
hmm.
So if you fix it this random seed and you will train your model, maybe you will get maybe 80% or 85%. It's okay. It is within the range. So it's correct,
Okay.
right? And you will use this model for solving your problem. But if you will publish your model, if you will put it in GitHub, maybe people will use it, they train the model, and people will be happy with the 85%. But if someone else, he said, now I have access to the data, I will retrain this model one more time, and he tried to retrain the model, he will get an accuracy within this range. But we don't know, I mean, what value. Maybe it will be too high, it will be too little, but anyway, it will be within this range, right? So in this case, your work will be correct because you don't claim that your model has an accuracy of 95%, and people found that it's 75 or 85 or 80%, because you will provide a range, you will provide mean value plus minus a standard deviation.
Yeah. All right. Okay.
You
Thank
will
you.
be safe. This is very important because if your model
Yeah.
will be used in healthcare, for example, for people should know that, okay, this one will be within this range. The accuracy should be maybe 95 or 80%, 90% plus minus 2% or 3%. So in this case, we can go to the upper bound and lower bound. It will be from lower bound to the upper bound, right? And this is because my loss function is non-convex. Because sometimes you will end up is in a local minima, and sometimes you will end up with this global minima. If you are ending up with this global, you are very lucky. But we need to be sure that when other people will retrain the model, they will be able to end up in the same this global minima, for example, not local. Because if they ended up in the local, they will say, okay, now you are, I mean, your results are not correct,
Yeah,
right?
but I'm thinking from another perspective. For
Mm,
example, if as you mentioned in healthcare system, right? So, for example, you trained your model, you put in your production system, and now your model is live, and you are, let's say, predicting with some disease, right? And you
mhm.
want to prevent your system to stuck up in the local minima because your wrong prediction might end up with severe consequences. So, in that case, is it better to fix a seed to avoid those local minima? For example, if your range is like 65 or 80%, so it's always too good to have a model around stuck maybe on the 80% rather than 65%, because in that case, if the model is stuck in local minima, your predictions would be wrong, and then it might cost you in
Yes, yeah, I agree with you. I mean, do whatever you want to improve the performance, and if you can, maybe you can use this random seed, and so you are now getting higher accuracy. Just keep those weights, but you need to
Okay.
tell people that if you will retrain this model one more time, maybe you will not be able to get the same accuracy,
Uh-huh.
right? But
All
but
right. Okay.
you can provide the model with the weights, and people can download the model because it's a trained model. So they will use like transfer learning. This model has been trained. Now we are able to achieve 95%. But just remember, if you try to retrain this model, we should expect something between this range and between this upper bound and lower bound, right? Just for your safety, because you are providing this model, and
Yeah.
maybe people will just accuse you that you are just
Hmm.
I mean fake results or something. So
Yeah. Yeah.
to be safe, you can have the model. I mean, I can achieve this accuracy, but just remember our accuracy will be within in this range. But in
Yeah.
fact, there are methods which we can use to avoid this non-convex. So we need to get out from this dilemma. In fact, so there are some in gradient descent also. There are some coefficient which we need to use to help us to fix this problem.
All right. Okay. Thank you. Thank you
Yeah.
very much.
I mean, this is just example. I mean, in this example here, we need to minimize. So this one should be x minus delta x, in fact, right? X equal x minus delta x, and the delta x should be this first derivative, which is the gradient. So delta x, in fact, should be maybe minus eta multiplied by the gradient of this function, right? So it would be minus eta, maybe this eta could be 0.1, for example. So we just need to select a random point. I mean, how this algorithm works, we need to start from a random point. Imagine that I'm starting from minus 10. By random, I selected x equal minus 10. So this is my initial point. So substitute this minus 10 in this function. So it will be minus 100 plus 2. It will be minus 98, correct? So substitute this value in this function. Imagine that eta is 0.1. So delta x in this case will be minus 0.1 multiplied by this value. It will be plus 9.8, correct? Now I need to update my x. So x equal old x, so it will be minus 10 plus 9.8. So it will be minus 0.8. So now we will move in that direction. So we next choice. So I'm starting from minus 10. My next choice, it will be minus 0.2. We will go to this point in that direction. So we are moving against the gradient, right? Because the gradient is moving in that. In fact, we are moving. Yeah. So it will be like this one. If you are starting from the opposite side, if you are by chance you are starting from 7.5 here, imagine. So what will happen? Substitute 7.5 into this equation. So in this case, delta x will be minus eta, which is minus 0.1 multiplied by f of x, f dash of x. So it will be 10 multiplied by 7.5. It will be 75 plus 2. It will be 7. So this one will be minus 7.7. So new x will be old x, which is 7.5, right? Minus 7.7, so it will be minus 0.2. So we will go directly into that direction, you see? So the most important here is that you will start from some location by random, by chance. Maybe you are starting from here. If you are starting from that side, we need to move into that direction. If you are starting from that direction, we need to move into that direction so we can reach this minimum point. And the eta here, it's a step size or learning rate. In fact, we call it learning rate. So the step size, it could be 0.1, 0.01, for example. It should be a small value because there are some consequences also if it's too small or too large. We will talk about it. So this non-stochastic gradient descent, it doesn't, there is no, it's not necessarily go to the optimum. You will get some results, but there is no guarantee that it is optimum, right? It's optimal, but it's not the optimum. So we have this non-convex function here, and we need to update weights, for example. So as I told you, if you are starting from here, we will be very lucky because we will go down to that point. Maybe we are not lucky, in fact, because this one it's local minima. If you are starting from here, you will go down here. If you are starting from that place, you will go here. If you are here, you will go here. So it's according to your initial weights, right? According to your initial weights, maybe. So, and therefore, I told you, you need to run your model several times because maybe in 50% of the cases we will start from here or from here, so we'll end up here. So maybe here we will get an accuracy of maybe 95%. And if you are starting from here or from that location, maybe we will get maybe 99%, for example. So you will see it. You will see the accuracy. And if you can see that each time we are getting a different value, you can understand that my loss function is non-convex. And in this case, I need to train my model several times. And I need to provide a range for the accuracy, not an exact value. And I prefer to do it, in fact, in all papers, in all models. I prefer that you report your accuracy as a range, not using a single value, because when it's a single value, chances for other people to get the same value, it will be very difficult. So the updating rule here, it will be delta omega. We need to calculate delta omega. So delta omega will be minus eta multiplied by the gradient of my function, omega t, for example, right? So, and you need to update omega. So omega equal omega plus delta omega. So we will do it like this. So the most important is to get a function which is differentiable. So your function should be differentiable because we need to calculate the gradient, and the gradient is the first derivative of your function. In reality, in fact, when we are working with simple function like this simple function, it's very easy. But when we are working with multi-layer perceptron or feed-forward neural network or a deep neural network model, the convex, the loss function will be very, very complex. As you can see here, it's in three-dimensional space. Maybe also it will be more complex than this. So as you can see here, if you are starting from this point, maybe you are ending here. Maybe you can go here, ending in this local minima. Maybe you will go here, right? Maybe you will go here. Maybe you will go here, which is local global minima, for example. So maybe you will come here, right? So in this case, you need to maybe fine-tune your optimizer in order to get the best accuracy of your model. So now we have this example, and it's just it's a very, very simple example, in fact. Okay, so I can share the link with you, so you can just run it, for example. So we have here a function, and this function, it's 5x squared plus 2x minus 4, as you can see here. So this function, it's f of x equal 5x squared plus 2x minus 4. If you want to get the solution analytically, calculate the first derivative, which is f dash of x equal 10x plus 2 equal 0. So in this case, the optimum value will be x equal minus 2 divided by 10. So it will be minus 0.2. So this is the optimum value, in fact. So we need to reach this point, which is the optimum value. So the function here will be minimum, right? Substitute this value in the function f of x. It will be 5x squared. So you will get this value, which is close to 0, for example, right? Or 0. So this is the optimum value. So if you want to solve it analytically, you need to get the first derivative of the function. You need to make this one equal to 0. Solve it when it's equal to 0. So x will be minus 0.2. So this one will be the optimum solution. If you want to solve this problem using a gradient descent, we need to calculate the gradient, right? So this one will be the gradient, df by dx. So this one will be delta, or gradient of x, or f of x. It will be x plus 2. And after that, we need to solve the problem for number of iterations. So we need to define number of epochs or iterations. And we need to calculate the gradient. And we need to calculate delta x. So delta x will be minus eta multiplied by this gradient, right? So it will be this one. It will be minus eta multiplied by df by dx. This one will be my gradient. You need to select a value for eta. Eta will be the time step. So I'm selecting the time step equal 0.01, for example. And just update x. So we need to start from some x value. So x, we will select x by random. Imagine that we are starting from x equal minus 90, for example, right? So it will take number of iterations. So we are starting from the side, and we will go into that direction. If you are starting from the side, we will go into that direction. So I can share the link with you, so you can open it in. You can just open it in Google Colab, for example, and try to. Okay. I will share it in the chat. You have it in the chat, please, so you can just open it. So it's just a very simple, just example, just to show you. So we will run it here. So now we are starting from, yes, I'm starting from random point. I'm starting from, yes, I'm just starting x as a random starting point from minus 10 to 10, for example. So as you can see here, the green point here, I'm starting from here. And we should be able to reach this red point. So we're starting from the green point, and we need to reach this red point here, which is minus 0.2. Now this is just to simulate it. In fact, this one is just to simulate it. Maybe I need to open it from here, I guess. Maybe this one. I'm getting it on my computer. Yes, as you can see here, we have this response here. So as you can see, yes, so we're starting from one point and we're reaching this optimum value using gradient descent. So gradient descent works very well, in fact. So we can go back to the slides. Yes, as you can see here, we are starting from some point and we can, yes, we can reach. So we're starting from x equal minus 90, I guess, and we can reach x equal. And as you can see, at the beginning, we move with high speed, and when we reach the optimum point, we slow down, right? Because the gradient is decreasing. So in fact, the gradient here is very large value. I mean, the gradient here, it's big value. And when we are reaching this point here, when we are close to the optimum point, the gradient is decreasing until it becomes zero. And when it's zero, we will not move any further because delta x will be zero. When delta x is zero, we will stuck in that place. So the problem here, if it is a local minima or global minima, if it's a local minima, we will stuck. We will not be able to move any further. We need to get some help. Yes. So the problem with gradient descent, weights are updated using this equation. So delta omega or m omega equal omega minus eta multiplied by this gradient of this function. So we can just say it's omega equal omega plus delta omega, and the delta omega equal minus eta multiplied by the gradient of this function, for example. So the problem here, learning will stop when the gradient of the cost function is at the saddle point. I mean, this delta omega will be zero. It means here delta omega will be zero when the gradient becomes zero. When the gradient equals zero, delta omega will be zero. And in this case, the learning process will stop, right? We will not be able to move forward if the gradient equals zero. To fix this problem, we need to introduce something called the momentum term. We need to add this momentum term to allow the optimizer to continue moving, so we can accelerate the optimization process. So if we have this local minima, we need to try to push ourselves using this momentum term out of it. And this momentum term, in fact, it's just beta multiplied by the last value. It will be this part. So we need to add that part here. So if you have omega equal omega plus delta omega, for example, plus delta omega. So we just need to add this momentum term, which is the last. We need to add the last value. We need to add coefficient multiplied by or percentage from the last rate of change or last omega, for example. So it will be omega equal beta multiplied by plus 2 omega plus 1 minus beta multiplied by the gradient, right? So we need to, okay. So we can say that it's omega equal omega minus eta multiplied by the gradient, for example, right? Or delta omega, or we can just say that omega equal omega plus delta omega. So in this case, delta omega equal minus eta multiplied by the gradient. So it's just we need to implement that part. We need to implement this equation. We need to calculate omega, which will be I would like to put it in the form of omega or the gradient. So anyway, the gradient will be plus 2 omega. So this gradient, it will be plus 2 omega, but multiplied by beta plus 1 minus beta multiplied by the gradient, right? So it will be like this one of omega. So in this case, if you selected beta, for example, equal maybe 0.5, so it will be 0.5 multiplied by plus weights plus 0.5 multiplied by the new gradient. So in this case, we can say that, okay, we need to keep momentum by adding the last updates, for example, 50% of the last updates. So momentum term will accelerate convergence, smoothing out oscillation, and escape local minima. We can see it here in a simulation. So we have this function, which is very complex function. I'm selecting this function because we have lots of local minima. We have one local minima here. We have also a local minima here, and we have here global minima. This one global. So the problem here, if you are starting from the side, it will be okay. We will go down here, which is perfect. If we are starting from that location, we will be happy because it will end up here. But the problem, if you are starting from here, maybe you will stuck here. If you are not stuck here, maybe you will stuck here. If you are starting from here, maybe you will stuck here, right? So it will be a problem. So in this case, in fact, if we have a loss function which looks like this function, and we'll try to find the value of x which will minimize f of x, the chances that we will end up as a value at 3.5, maybe we will end up at 3.5, maybe we will end up here at 1.3, for example. In fact, the reality we need to be here at minus 4.8, for example, because this is a global minimum. So we need to fix this non-convex function. We need to minimize this non-convex function. So in this case, we need to implement momentum term. Momentum term will help us to escape from this local minima. So I try to use, because I need to get the first differentiation. So I need to use a function in Python, which will help us to get the gradient, for example. So I just need to define x as a symbol. And after that, you will define your function, which is f of x. It will be this one. Because it's the first derivative, it's difficult. So I need to use a library for doing this. So the first derivative will be fx dot differentiate with respect to x. It will be this one. So now I have f of x, which is my function, and I have also the gradient, which is df by dx, right? So we got this df by dx. So I will train my model for 10 epochs or 100 epochs or 100 iterations. I need to define the eta, which is the learning rate, and I need to define also beta, which is the momentum term. I will start first with 0, and after that I will try to increase it and see what will happen. And I just here maybe I start with some random points for x. So maybe we will start from the negative side and we will start from the positive side. So when it's positive and then when it's negative, we will test it. And after that, we will train our model for number of iterations. And as you can see here, we try to calculate delta x, which will be eta multiplied by the first derivative, right? Plus beta multiplied by the last delta x. So we will calculate delta x. So we will calculate delta x. So delta x will be eta multiplied by the gradient, which is plus beta multiplied by last delta x, in fact. So it's delta x old or something, right? We need to just say it's delta x old, right? Last one. And you need to update x, so x will be x minus eta multiplied by this delta x. And after that, you need to update delta x, because I need to store it in somehow. So once you calculate this delta x, just store it in something we call it delta x 0 or delta x old. Just store it in somewhere. So now we will test our model. So as you can see here, yeah. So you see it? When we are starting from here, we will end up here. Now we have this beta equals 0, in fact. This momentum term equals 0, but we are okay here. We don't need it because we are starting from here. So we will end up here at that location, which is very good. We will go to the second model also when beta equals 0, but you are starting from here. When you are starting from here, what will happen? You will stuck here, in fact, right? So you see? Okay. So we are starting from here. We will end up here. In the left-hand side here, right-hand side, we are starting from that point, and we will end up here. So it's okay, but we stuck here in this local minima. So maybe here, if you are training your multi-layer perceptron, here you will get an accuracy maybe at 95%. In this case here, maybe the accuracy will be 80%. So we have a problem here. How can we fix it? We will try to introduce this momentum term, and I will use this beta equal 0.5. If you are starting from here, no problem. because it will try to push you further to the right, but you will go back, right? You will go back. So do you see here? We ended up here, but because we have momentum term, so this momentum term, it will help me also to try to escape from this one. Because in reality, I don't know if this one is local, minima, or global. My model does not understand this. So the momentum term, it will try to push me out, but it's not strong enough, and I will go back again to my global minima, which is very good. We will try it with the other example here. Do you see? We add here beta equal 0.5. So we will try to go out from this one, but it's not strongly enough. So I will try to escape, but I went back again to the same point because this ratio maybe it's not big enough. So in this case, maybe we need to increase this one, maybe to 0.6 or 0.7. So now I will try it with 0.9. Yes, we are starting from this point. Do you see? And I used momentum term equal 0.8. So in fact, this 0.8, it was good enough to take me out from this local minima, but we stuck in the second local minima here, right? Because this momentum term, it was not very big enough. So in this case, maybe we need to change it, and I need to increase this momentum term one more time. When we increase it, what will happen? Do you see? Now we are able to escape this local minima. We are able to escape the second local minima, and now we can reach this global minimum. So now we are perfect. Now we can get an accuracy, maximum accuracy, which we can get. So in fact, if you have this non-convex loss function, also, if you can look into this right figure here in the left, one in the left, we are starting from here, and we are using beta equal 0.9. So in fact, the model doesn't understand, I mean, if this one is local minima or global minima, so it will try to push it out. Yes. Yeah, it will try to push it out from this global minimum, but it will go back, right? Do you see? It will go back again to this point. So the idea here, if you discovered that you have this problem, you have this non-convex loss function, and each time you will get different accuracy because of this, non-convex nature of your loss function. In this case, you need to make some changes to your optimizer, and you need to use momentum term. This momentum term is very useful because it will help you to get the same accuracy each time. So in this case, if you will use momentum term, and if you run your model maybe 10 times, you can fine tune this momentum term, and you can each time you will be able to reach high accuracy. So in this case, maybe the accuracy will be 95% plus minus 0. Standard deviation will be 0, right? If you will use this momentum term equal 0.9. Maybe if you will use momentum term equal 0.6, maybe in this case you will be able to reach an accuracy of 93% plus minus 2%, right? If you will use momentum term equal, so each time you need to test, and you need to fine tuning your hyperparameters, because this momentum term, this coefficient will be hyperparameter. So you need to fine tune your model, and you need to select this hyperparameter in a way to maximize your accuracy. In this case, we have very good accuracy because it's just 95% plus minus maybe 0.1%. So the range is narrow. It becomes narrow now because now we can achieve much better accuracy. So if someone else will use my model, he will train your model in India or in China, for example, he will be able to reach the same accuracy if he will use the same setting. There is something called ADAPA, or adaptive learning rate, for example. We have also the optimizer. If you use this adaptive learning rate, what will happen? We can use eta, for example. This is my learning rate. It's just eta. So as you can see here, we are moving with the same speed, right? We are moving with the same speed. But if instead of using eta, maybe I can use eta as a function of number of iteration. If you multiply eta by I, divided it by I plus 1, for example. So in this case, if I equal 0, so we will, in the first iteration, we will start with eta. But if I equal 1, it will be eta divided by 2, right? So it will be eta divided by 2. In the second iteration, the learning rate will be 2 eta divided by 3. So it will be 2 divided by 3 multiplied by eta, and so on. So you will start with large eta, and you will end up with very, very small learning rate. And it's very important because in some cases you can oscillate around the optimum point because the learning rate is very high. So it's smart to start with a large eta, and with iterations, this eta value should decrease. So you can use this formula, for example, eta multiplied by I divided by I plus 1, or just eta divided by I plus 1. So in this case, it will be, we will start with eta, when I equal 1, it will be eta divided by eta, eta divided by 2, eta divided by 3, and so on. So the value of the learning rate will decrease with iteration. So now we can see the impact. If you are starting with just eta, and if you are starting with this formula, for example, so you can see that you are moving at, you minimize your function with high speed, with larger step size at the beginning, and speed will decrease when we are close to the optimum point or the global minimum, for example. Do you see? So in this case, we will avoid oscillation, because maybe in some cases people will just go here and it will go here and it will go back here. So we will oscillate around this global minimum, for example, because I'm using very high learning rate. So the best option is to use this adaptive learning rate, where we start with a large eta, large learning rate, and after that, this learning rate, it will decrease with time. So when we try to reduce the speed when we are reaching our optimum solution or optimum point. So now we finished this. We talk about this stochastic gradient descent because it's very important, because we can use something called adaptive linear unit or adaptive linear algorithm. For example, it's a kind of a perceptron which can be used for regression, for example, right? So if you use this hard limb function, if you will use this symmetric hard limb function, for example, so in this case we will use perceptron learning rule. But if you will use this function, which is linear function, so in this case, in fact, we need to use maybe stochastic gradient descent. We need to use stochastic gradient descent to adjust the weights of this adaptive linear unit algorithm. And this adaptive linear unit or adaptive linear neuron, we use it for regression problems. And it's exactly the same as a perceptron, but we need to change the activation function from hard limb or symmetric hard limb into linear. This is the idea here. Not only this, in fact, you can use different types of activation function. You can use sigmoid, you can use hyperbolic tangent, correct? If you want to use also this function rectified linear unit or leaky rectified linear unit, exponential LU, for example, there are many activation functions which you can use. The most important here is to define your loss function. Your loss function must be convex. So this is my loss function. It will be summation of t minus y squared, right? T minus y squared. We square it because when we square it, we will be sure that this function will be convex, right? And we multiply it by 1 divided by 2 because this is the loss function. If you want to calculate the gradient of this function, it will be the first derivative with respect to y. So we need to take the first derivative of this function. So it will be 2 multiplied by this one. So we multiply it by 1 divided by 2, because when we take the first derivative, it will be 2 multiplied by this one. So it will be summation of t minus y, right? So I mean, 2 will cancel the 0.5. So in this case, it will be the first derivative. It will be like that, but we don't care. Just multiply it by 1 divided by 2 or not. It doesn't make any change for us. So now we need to solve this one. If you have this adaptive linear neuron, you want to use it for a regression, for example. In fact, we can use it for regression, and we can use it also for classification. If you want to use it for regression, we will cancel that part. We will get the output directly from here, right? So you have some inputs, maybe those inputs, it's age, it's years of education, and so on, and you want to regress your income next year, for example. You need to predict the income with those qualifications, what will be the income. So in this case, we will use the output from here directly. If you want to use it for classification, we just need to add this threshold value. So we will calculate the output here, and after that we will say, okay, maybe images with 0.5 or higher, it will be classified as dog. Otherwise, it will be classified as a cat. In this case here, we have linear activation function. It's linear activation function, so we need to define a lot. We cannot train this model using perceptron learning rule because the activation function here is different. We use here linear activation function. In this case, we need to define a loss function. This one will be my loss function. So this loss function will be summation of t minus y squared. multiplied by 0.5. So this one will be my loss function. You need to define it. And to adjust your weights, we will use a simple rule, omega equal omega plus delta omega. And the delta omega, we will use gradient descent. So delta omega will be minus eta multiplied by the gradient. So this gradient, it will be the first derivative of this function with respect to omega, because we need to adjust weights, right? So we need to calculate the first derivative of this function with respect to omega. So it will be, we will use something called the chain rule, because this is my function. I need to get partial j by partial omega, but this function is not function of omega. So I will calculate partial j by partial y and multiply it by partial y by partial omega. That is it, right? Remember, t is the target, so t is constant. So what is partial j by partial y? Partial j by partial y, it will be 2 times half. So it will be summation of t minus y, correct, multiplied by the derivative of t minus y. First derivative of t, it will be 0. First derivative of y with respect to y, it will be 1 multiplied by negative, so it will be like this. It will be negative summation of t minus y multiplied by partial y by partial omega. What is y here, right? Y here, in fact, equal omega x plus p, correct? So the prediction, it's omega x plus p, because the summation here, y is just y here. So y here, it's omega x plus bias. What is partial y by partial, what is partial this function with respect to omega? It will be just x. So this one will be multiplied by x. So this one, in fact, it will be partial j by partial omega. Equal that part. Now we need to calculate delta omega. So delta omega will be minus eta multiplied by that part. So minus minus, it will be plus. So it will be eta multiplied by this function, summation of t minus y multiplied by the input x. Right? So now we will do it for delta omega. If you want to do it for the bias has an input equal plus 1. So it will be the same, but this x will be just 1. So delta b will be eta multiplied by the summation of t minus y. Right? So I hope that it's clear. So now if you are starting from this point, you will go into that direction. If you are starting from this point, you will go into that direction. It's the direction which increase the value of x. I mean, if you are here, so we need to go into the direction which increase the value of x or omega, right? Because here, so we need to go move into the, if you are starting from here, we need to move in the direction, which will decrease the value of omega, right? Because here, the gradient here is negative, but the gradient here is positive, correct? So we need to move against it, right? We need to multiply it by negative. Yeah, because here it's positive, here it's negative, right? The gradient or the slope here of this line is negative, but the slope here is positive. So here we need to multiply it by negative, so we can move in the direction which will decrease the value of x. So I started here by value of x. So in fact, delta x must be negative, right? So it will be minus eta multiplied by the gradient, and the gradient here is positive. So negative multiplied by positive, it will be negative. So in this case, we are sure that we will move in that direction. If you are here, in fact, you are starting from negative value, and the gradient is negative. So negative multiplied by negative, so delta x here, it will be positive. So in this case, I will move from that direction into, so I will add some positive value to this negative value here, so we can go into that direction. So delta x here must be positive. Yes, so maybe we can solve it, right? So we can just do it for sigmoid or any function you want. We don't care, right? Any function, if it is maybe a linear function or maybe a logistic function, for example, it will be okay. So this logistic regression is very similar. This one, it's adaptive linear unit. So we are using this function, linear function. If you can just change this function with another activation function, which is this logistic function, sigmoid, it will be the same, but we will call it logistic regression classifier. but it's exactly the same. Logistic regression classifier. It's a classifier because the output from this model will be a number between 0 and 1 here. You see, because the output from this logistic function or sigmoid function, it's a number between 0 and 1. So in this case, we can just assume that the number which we will get here, it's the probability. So in this case, when it is probability, we can use this one for classification. So that we call it logistic regression classifier because we will get a probability because we are using this activation function here. You will get a number between 0 and 1, and you can just say that, okay, now, if this number is greater than 0.5, this image will be classified as a dog. Otherwise, it will be classified as a cat. But this adaptive linear unit here, it's just, we use it for regression, correct? So we will get a number here, a scalar value. If you want to predict my income for my qualification, so we need to get a number here, which should represent your income, for example, your expected income. And after that, if you want to classify it into rich and poor, you can use a threshold function. So people who are earned more than maybe 1 million NOK, they are rich, otherwise they are poor people, for example. And in this case, all of us are poor. Yes. So for this logistic regression classifier, we just replace this activation function with logistic function, and we will do the same exactly, right? We need to calculate net, right? So net will be omega x plus b. Just remember, we need to have here bias, right? If you don't have bias, just try to include it into, yeah, we are including it here into this one, in fact, right? So it's omega 0 multiplied by 1. So now we have bias included in the input. So net would be omega transpose x, or omega x plus b. So we need to get the output from here. So this output here, we call it G net, for example, or f of net. It will be this logistic function, or it will be 1 divided by 1 plus exponential minus net, right? And you calculate net. So first you need to calculate net, and to calculate the output here, you need to substitute this value into this function, logistic function, or sigmoid function, right? So it will be 1 divided by 1 plus exponential minus net. You can add those hypotheses for classification. Y will be 1 if y will be 1 if this value is greater than or equal 0.5. Otherwise, it will be 0. So just 1 second, please. I have. Okay. So yes. Break 10 minutes. 10 minutes. And start again after maybe 11, maybe 25 or something, or 11, 20. Is that okay?
Yes, it is okay.
Okay, thank you very much.
Yeah.
Thank you.
Thank
Bye-bye.
you.
Bye-bye. Hello, everybody. I'm really sorry for disturbing you today. Yes, we can start again, and if it is possible, if we can finish today at 12, it would be great. So we have only 30 minutes left. I'm so sorry again for this today. It's just some issues here.
No worries, I
So,
think it's fine.
okay,
Yeah.
so I apologize really for today. Okay, so now we will go to this model one more time, this logistic regression classifier. So this logistic regression classifier, it's very similar to a perceptron or adaptive linear neuron, except that we use different activation function. And once you have this activation function, we just need to get the differentiation with respect to this activation function. So for example, if we need to train this model, we need to update omega. So we need to get delta omega. So omega will be omega plus delta omega. It's the same rule, delta omega equal minus eta multiplied by the gradient of the error function, right? We need to define error function. So error will be 1 divided by 2 multiplied by summation of t minus y square, right? We need to get this gradient. So this gradient, it will be partial e by partial omega. So it will be partial e by partial y multiplied by partial y by partial omega. We have this partial e by partial omega, we did that already, so it will be negative summation of t minus y multiplied by partial y by partial omega. Y equal this one. Y equal 1 divided by 1 plus exponential minus net. So we just need to get the differentiation by with respect to net. So it will be, in fact, partial y by partial omega. We need to do it using the full chain rule. So it will be partial e by partial omega multiplied by partial y by partial by partial y multiplied by partial y by partial net multiplied by partial net multiplied by partial. So we will use this chain rule. So we need to get partial y by partial net by getting this y dash, this function, and after that partial net by partial y net equal omega x plus b. So this one will be just x, and we can solve the problem. So in the perceptron, we update the weights after each individual training sample because we use the perceptron learning rule. But here, in fact, we can use stochastic gradient descent or batch gradient or mini batch gradient descent because we are using a gradient descent. So in this example here, in this logistic regression classifier, we don't need to update the weights after each example using stochastic gradient descent, but we can use because we are using because we don't use here a perceptron learning rule. Here we are using a gradient descent, and when it is gradient descent, we can use stochastic gradient descent or batch or mini batch gradient descent, right? So the training mode, stochastic gradient descent, we call it online learning. Now we understand it. So we will do learning process example by example, and it's good for systems. When you have a system implemented in maybe edge device, for example, and you are collecting data in real time, so you don't need to collect the data, and after that you will train your model. But once you have new data coming in, you can just train your model, and that is it. You don't need to store the data and train the model later on, but you can just train the model example by example, and therefore we call it online learning. It's good when you don't have enough memory. Batch gradient, we calculate the gradient based on the whole data set. So we have this average gradient, and we will use this mean gradient for adjusting the weights. So it will be according to the batch size, for example. So mini batch gradient, the batch size usually it's the whole training data set size. In case of mini batch gradient, we divide the data into mini batches due to memory restrictions, and we do this mini batch gradient learning process. If you will use large learning rate, it may overshoot the global minimum and fail to converge, and maybe it will diverge, in fact, right? So similar to this example, as you can see here in this example, you have very large learning rate. So we need to reach this point, but we cannot reach it because the learning rate is very high. So we try to isolate around this global minimum. We will not be able to converge. So we just go from that direction to here, from here to here, like this one. And we will not be able to converge because we have very large learning rate. If you have very small learning rate, in this case, you will be able to reach this global minimum, but it will take many iterations. This is a problem. So if you selected very, very small learning rate, it will take too much time to reach this global minimum. So if you selected it very large, it will be a problem. If you selected it very small, it will be also a problem. So the most optimum way is to use this adaptive learning rate, where we start with large learning rate, and after that, we will reduce it with time. So you can just, instead of using eta, for example, you can just use eta divided by I, where I is the iteration number. So when I equal 1, it will use eta. When I equal 10, it will be eta divided by 10. So in this case, it will reduce the learning rate with time. So in this case, we will start with very high speed, and we will lower the speed when we are close to the minimum optimum point. We have here implementation of adaptive linear unit. So it's just we try to use iris dataset as we did before. We have iris dataset, and we will select two inputs because we need to plot this data in. We will select two features, 0 and 2, right? Because we need to plot it in two-dimensional space, and we will select the first two classes. The first two classes corresponds to the first 100 points. So after that, we will try to define this adaptive linear unit. So this adaptive linear, we need first to initialize our model. So we need to select a number of epochs, learning rate, for example. So those are default values, for example. And after that, we will define a function for prediction. And then when you need to predict, you just need to apply inputs to the model and get prediction. So it will be like this one. It will be omega x. When it is adaptive linear unit, it will be like this one. So we have two inputs, maybe x1 and x2. This one connected by omega 1, omega 2. We have here bias. We will calculate summation, and after that, we will have this linear function. Right? So it will be like this one. So in fact, if you want to get y, so y will be omega x plus p. So it will be like this one. So net equal input multiplied by weights plus bias. So this equation, in fact, it's omega x plus p. We call it net equal omega x plus p. And after that, we will apply this linear activation function. So, or in fact, this function, it's hard limb, this one, right? So this one, it's this function, right? So we can say that, okay, if net greater than or equal 0, the output will be +1, otherwise it will be -1. So in this case, we are applying this function, not this function, sorry. It will be this symmetric hard limb. It will be this function, because we need to classify, because in this problem we have in iris dataset, we have two classes. So we need to get output as binary, so it should be +1 or -1. So first we will calculate net, and once we have net, we will apply this net to this activation function, and it will convert it into +1 or -1. So this is the predict function. We have training. We need to train this model. To train the model, you will, for each iteration, first we need to initialize weights. So we will initialize those weights with random values, right? Because I don't know how the loss function looks like. Maybe the loss function looks like this. So we need to start from some location first. Maybe I need to start from here or from here or from there. So to decide this, we need to select it by random. So we need to initialize those weights by random. So it will be random values. And after that, for each epoch, we will calculate the net value. So net will be omega x plus p. This one net equal omega x plus p. And after that, we will use this linear activation function. So y equal net. And once you calculate y, you will calculate the error value, right? Error will be t minus y. And after that, I will use gradient descent for calculating the weights. So, so delta omega, you can see here delta omega equal eta multiplied by error, correct? Multiplied by x. So it will be eta multiplied by error multiplied by x. And this is what we will get in fact from gradient descent when you are using this linear activation function. So it will be eta multiplied by t minus y multiplied by x, right? If you want to get it, so you need to just define your cost function. So error will be 1 divided by 2 summation t minus y squared, correct? We need to get delta omega. So delta omega will be minus eta multiplied by gradient of e. So this gradient, it will be this gradient of e. It will be partial e by partial by partial omega. So it will be partial E by partial Y multiplied by partial Y by partial omega, correct? So so it will be partial E by partial Y, it will be 2 times a half, so it will be negative. So I mean this delta omega, or the gradient, it will be 2 times a half, it will be 1 negative summation T minus Y multiplied by partial Y by partial omega. In fact, Y equal net, and the net equal omega X plus B. So partial Y by partial omega, it will be just X. So as you can see here in this equation, it's eta. In fact, it's eta multiplied because delta omega will be negative eta multiplied by partial this gradient. So negative, it will be plus. So delta omega, it will be eta multiplied by T minus Y multiplied by X. And it's very similar. In fact, I mean, this equation, when you look into this equation, it's very similar to a perceptron learning rule, because in perceptron learning rule, it was eta multiplied by error multiplied by X. And the error here is T minus Y, if you want to make it like this. So first we need to calculate delta omega. So it will be eta multiplied by this error multiplied by X. And if you want to do it for the bias, so it will be eta multiplied by error, only error, because the input to the bias is +1. So we will calculate delta omega, and we will calculate delta B, for example, and we will adjust weights. So omega equal omega plus delta omega, and the B equal B plus delta B. If you want to calculate your prediction error, so that because I need to, for each epoch, for example, we need to calculate the error. So we need to just define a function to calculate the cost function or the error, for example. So it will be half multiplied by T minus Y squared. You just take the summation for each epoch, because in each epoch we will use a stochastic gradient descent. So in this case, in each epoch, we will apply the whole 100 points. So in this case, you just calculate the mean of error for each epoch, and you can plot it, for example. So we will do this here, and we trained the model using the first 100 points, and finally we got those errors. So the error at epoch number 1, it will be this large value, because we are starting with some random weights, and after that we will adjust the weights, and when you adjust the weights, it will be adjusted in a way which will minimize the error. So in this case, we can minimize the error. So at epoch number 10, for example, we got error equal almost 0, right? Which means our model will have an accuracy of 100%. So if you want to plot your decision boundary, for example, we did that last time. So you can get the value of omega 1, omega 2, and the B, and you just find the net. So it will be omega 1, x1 plus omega 2, x2 plus B equals 0. This one will be my decision line. You need to assume values for x1, for example, this is x1, and this one is x2. So just to try to generate values for x1 using this function, arrange. And after that, substitute these values into this equation to get x2. So x2 will be minus omega 1 divided by omega 2 multiplied by x1 minus B divided by omega 2, right? So you will get x2. So now we will just substitute those values into x2, and we will plot x1 and x2. So we will get this decision line, right? So now we can classify this problem using adaptive linear unit. So the problem here, this system or this approach is very sensitive to the learning rate. So if you change it, if you increase the learning rate a little bit, what will happen? Your system will diverge, right? It will diverge. And we know the problem here. I mean, if you want to fix this problem, maybe we need to normalize or standardize your input features. When your system is sensitive for the learning rate, so in this case, it means that you need to work a little bit on your data. We need to standardize or normalize your input features. So how to improve gradient descent using feature scaling? We need to do this feature scaling. So standardization, we need to shift the mean and the variance of each feature so that it's centered at 0 and has feature standard deviation of. So we just apply this equation. Take each input or each x, we need to subtract each x from its mean value and divide it by standard deviation. So x will be x minus mu divided by sigma. In this case, we try to standardize all inputs. So in this case, it will have a mean value equal 0 and the standard deviation equal 1. If you try to train your model with the same learning rate maybe, and even much bigger, but with the scaled features, the performance will be much better, as you can see here. So when you do the standardization or normalization, the performance of your model, we will train the model using X normalized, and in this case, you will get better performance, and your model will be, it will be much better trained and smooth, because when we standardized all inputs and normalize it, the model will deal with it as all will be dealt with as more fair way, in fact. So use adaptive linear unit to predict salary, for example, if you want to use it for predicting a salary. So this is years of just I try to create this data set for myself, in fact. So I'm expecting that if you have those years of experience, your salary should be this red points. And we'll try to build a model which can predict my income, for example, next year or after 10 years of experience. So for example, if you have 4 years of experience, you should get this salary. Maybe if you will have 8 years of experience, what should we expect your salary will be? So your salary should be this one, for example. So in this case, we need to train a model for doing this. So it's just one single input, years of experience. Your model is very simple. It has only one input, which is years of experience, and we need to use this adaptive linear unit for predicting it. You can use a regression model, of course, and you can use adaptive linear unit, and we will get those weights and the bias, because we didn't, in fact, normalize or standardize my data. So we have this example. You can just go to this example and try to play with it, please. This is just for different learning rates, for example. If you use, for example, here, very small learning rate, the model will take more time, in fact, to converge. So it will take maybe 500, maybe 5,000 epoch to converge. But if you try to increase the learning rate a little bit, what will happen? It will converge faster, right? You will get the same results, but your model will converge faster. So in fact, this learning rate, very, very important hyperparameter, which we need to play with. Here we need to talk about some activation functions. So the activation function can be divided into maybe linear activation function and a non-linear activation function. So for example, we can use unit step, which is hard limb or symmetric hard limb. This one, it's hard limb, which will try to squeeze inputs or outputs from number between 0 and 1, for example. So the problem here, when you try to take the first derivative of this function, it will be a pulse function like this one. And this pulse function has very bad response, in fact, with a gradient descent. So it will be this function. If you have sigmoid, maybe this is a sigmoid function, which is exponential. Well, it's 1 divided by 1 plus exponential minus x. You can multiply the numerator and the denominator by exponential x. So it will be exponential x divided by exponential x plus 1. So anyways, this is the function. And this is the first derivative of your function, right? So the gradient, because if we have this function, if we use this function in my model, it's non-linear function. But if you want to use this function for, classification, for example, or something, so the gradient will be decreased into this function. This one will be the first derivative, right? This is the first derivative of this function. So you can see that if we use this function as an output function, when we propagate the error through it to the next layer, we will get only this amount of error, right? So you will get this one. And if you are using 2 layers, for example, so maybe it will be multiplied by another small value, so it will get smaller. So the problem here when we are using this sigmoid function, it has this squashing effect. It has this squashing impact on the outputs, right? So it will try to compress the output between a number between 0 and 1. So when you are using this function, it's very important to normalize your inputs. Very, very important, because it squash inputs to arrange between 0 and 1, right? So imagine that you are using this. Usually we have this function here. We calculate omega x, right? Omega x 1, 2, for example, we have bias, so we calculate this net value. And when we are using this function here, it will squash all those net values into a number between 0 and 1. So imagine that x1 is income, for example, and it's in 1 million, in millions. So millions multiplied by omega, it will be squashed into a number between 0 and 1. And imagine that x2, its age, for example, or years of experience. So we will have a problem here, in fact, when we are using this function. It will squash all those inputs into a number between 0 and 1. And in this case, in fact, we will try to destroy my data set because we will not be able to see the impact of my data set because we squashed all those inputs into a number between 0 and 1. And it has, so this is one side effect, in fact, squashing effect of inputs. So if you want to use this function in a model, it's very, very important to normalize x1 and x2. So all those x1 and x2 will be a number between 0 and 1. So it can be represented here. So we don't destroy the variability in my model, in my data. So we will see, okay, someone has an income of 1 million, he will be here. One has an income of 20 million, he will be here. But the problem, if I didn't normalize all inputs, maybe all people with income higher than 5 NOK, all people will be represented here, right? So this is a problem. So now we are destroying the variability in my input feature if we will use this function without normalization. So the idea here, if you will use this function in your model, you need to normalize x1 and x2. If you didn't normalize, maybe you will lose most of the information in your data set. It will be lost anyway. You will lose it in somehow. But if you try to normalize, we will keep those variations and it will make impact for my maybe classification or regression problem. We can use also softmax and its normalized exponential function. And the softmax calculates probability distribution of the event over n different events. It's very important, this softmax function. We use it when we are working with multi-class classification problems. So maybe when you have an output layer, and in this output layer we have multiple classes, maybe 3 classes or more, for example. So in this case, we will use softmax. And in this case, the summation of the output will add to 1. Right? So I classify into A, B, and C. So maybe one of them, the probability or the output from one of those will be 0.6. Maybe the other one will be 0.2. The other one must be 0.2. So summation at the end will add to 1. Right? So in this case, I can say, okay, this is class A because the probability is 0.6. So the range will be from 0 to 1, and the sum of all probabilities will sum to 1. The softmax function used for multi-class classification model, and it will return the probability of each class where the target class will have the highest probability. So we can use argmax, right? So if you are using this softmax layer, for example, softmax layer, it will be the output layer. We call it softmax layer because we use activation function softmax because it will calculate the probability. And once you have the outputs, you can use this argmax function to get the right class. We don't use it for a single variable because it doesn't make any sense, because it will be sigmoid, in fact, in reality, because when you normalize a single value, it will be just the same value, right? So it doesn't make sense when you use it for a single output. So we can use also a hyperbolic tangent, and the hyperbolic tangent, it's like this one, and it's exponential x minus exponential minus x divided by exponential x minus plus exponential minus x. And the first derivative of this function will be 1 minus hyperbolic tangent square. So it will be 1 minus tan h square. So it will be this one. And in fact, this one has better performance in terms of gradient, vanishing gradient problem. So if you have a chance to use hyperbolic tangent, it will give you much better performance compared to sigmoid, because this one has better gradient. The gradient has better value here. It reaches 1. But the other one, it was 0.2. 0.3. So this here, when we use this function for calculating the gradient, it will give you small value. But if it is hyperbolic tangent, it will give you much better performance, right? It will give you better performance. So this function, in fact, it will give you much better performance with respect to vanishing gradient. You can use also rectified linear unit, and this rectified linear unit is this one. It's this blue one, right? So it's very good. And in fact, it's very simple. It's just a max between 0 and x. So if your input is negative, you will get 0. And if your input is positive, it will be the same value. So it will be this blue part here and this. So any value will be converted into the same value if it is positive. And if it is negative, it will be converted into 0. And we use this ReLU effect we use this function in deep learning, because in deep learning we are working with images, and all pixel values in images are positive values. We don't have any negative pixel value. So just use this one without normalization, without anything. this one will give you the best performance. And when you differentiate it, it will be a problem. So we need to have the softmax. We need to approximate it using this function, which is called soft plus. We call it soft plus. So we need to simplify it using this soft plus, because this soft plus, it will be smooth approximation to this rectified linear unit, and it's differentiable. When you differentiate it, you will get this one. So this one will be the soft plus function, and then when you differentiate it, you will get this one. And then when you differentiate it, it will be in fact this sigmoid. So the first derivative of the soft plus function, it will be this sigmoid. So the performance will be much better in terms of vanishing gradient. So you have this code, in fact, and you have all those functions, how to plot those functions and how to get the first derivative of those functions. So differentiation, of course, it's very important because we need to calculate the gradient. So, and this gradient, it will be the first derivative of this function with respect to x or with respect to omega. So it's very important to select a function which is differentiable. I mean, it's just an example. Again, if you have this function y equal x squared minus 2x minus 3, you need to find x which will make y of x minimum. So just to differentiate this function, set this one equal to 0. So in this case, x equal 1. So in fact, this function will be minimum when x equal 1, right? If you want to solve it using a gradient descent, you need to get the first derivative. We will call it the gradient. So the gradient will be 2x minus 2. And after that, you will use our rule. We need to calculate delta x. So delta x will be minus eta multiplied by this gradient, right? Which will be here 2x minus 2, right? And after that, update x value. So x will be x plus delta x. We just need to apply this rule. And in this case, you will be able to reach this optimal point after a number of iterations. So there are lots of activation function. So this is the different activation functions which with each first derivative. So we have this linear function, and its first derivative it will be just 1. This hard limb function, and it's a problem. In fact, this function, you have this logistic function or sigmoid. So this is the function. This is the first derivative. It will be f times 1 minus f, hyperbolic tangent, for example, and so on until we have this soft plus, right? And this is the first derivative of the soft plus function, which will be a sigmoid. If you can compare this one with this one, you see, right? So in fact, the first derivative of the soft plus is a sigmoid function. So in fact, this function is the best. When you are working with deep learning models, it's preferred to use the soft plus because the soft plus, it's differentiable, and at the same time, so you will be able to use gradient descent, and at the same time, its first derivative is a sigmoid, and this sigmoid, it means the error value will be a number between 0 and 1. It will be like this one. It will be a very large value. So the performance of this function will be much better with respect to vanishing gradient. So this is many functions and its first derivative, for example. So or those functions, we have sigmoid, we have hyperbolic tangent, rectified linear unit, soft plus, and the Gaussian. This is just a comparison between rectified linear unit and the Gaussian. So if you have this sigmoid function, so you see its first derivative, it will be this one. It will be this shaded part, which is very small. You see? So maybe the maximum output here, it will be 0.23 something. And if you are using this function in multiple layers, and we will do this multiplications, because when we propagate the error from the output layer to the input layers, we need to propagate through many different layers. So in each layer, you will do this multiplication several times. So at some point, it will be 0.2 multiplied by another 0.2 and so on, which will get much smaller. So the problem here, when you are using this Gaussian activation function, at some point, this delta x will be 0. Delta x will be 0. And then when it's 0, you will not be able to adjust your weights. And if you cannot adjust your weights, what will happen? You will keep the random values which you started with, right? So imagine that you have a feed-forward neural network, and you can adjust the weights of the output layer and maybe the last hidden layer. But maybe one of the hidden layers, I cannot adjust it, or the input layer, I cannot adjust the weights, because because the delta omega becomes 0. So in this case, we will keep those initial values, which we started with, which are random values. So in this case, I will keep multiplying my input features with random values. So it will be random values. So in this case, in fact, we are training our model with noise, with random values. Because random value multiplied by any value, it will be a random value. So you can just imagine that I train my model to classify images using, for example, random values, using noise. So it's very important to avoid this vanishing gradient problem, because if you will have it, you will have some weights which will not be able to train or to adjust. But if you will use this softmax, which is this dotted function, this blue one, the first derivative of this function will be a sigmoid, you see? So which is shaded now. So it's much larger, right? So if you can calculating the gradient using this function, you will get much bigger gradient. So this gradient value, it will be enough. It will be big enough to adjust your weights. But if you use a sigmoid, you will get this small contribution. And this small contribution, it will get smaller, in fact, if you have deep model where you have multiple layers. If you have multiple layers, you will do multiple multiplications, several multiplications. And at the end, this gradient will get smaller and smaller when you reach the input of the top part of the model. And in this case, you will have this vanishing gradient problem, which will prohibit you from adjusting all your weights. At some point, delta x will be 0, and when it is 0, it will be a problem. But using this softmax activation function, you will have much better performance because the gradient here, it will be much larger. So the vanishing gradient problem, it happened when we train artificial neural network with gradient-based learning method. So we are subjected to it, in fact, if we are using a gradient descent approach and the backpropagation. And it describes a situation where a deep multi-layer feed-forward neural network or a recurrent neural network is unable to propagate useful gradient information. This gradient information will be very, very small from the output to the input end, right? So because we try to propagate it from the output end of the model to layers near to the input. And if this gradient becomes very, very small, those layers closer to the input will not be able to adjust weights. And it will not be able to learn, for example, from my data sets. And what will happen at the end? What will happen that partial E by partial omega, it will be close to 0. And then when we adjust the weights using this formula, delta omega equal minus eta multiplied by the gradient, it will be also 0. So omega equal omega plus delta omega. So each time it will be just omega plus 0. So in this case, we will not be able to adjust weights. So what will happen if it is an input layer? This input layer, in fact, it will receive inputs multiplied by weights, but those weights are still the initial values which we used at the beginning, and those initial values, we selected them by random. So this layer, in fact, it will see only random values. So imagine that you have an inputs, and those inputs are coming from an image, for example, or maybe your salary, your age, your years of experience, and you just multiply those important information by random weights. So all time your weight will be able to see just random values or just noise, not true values. So when we have this problem, in fact, we are destroying, in fact, my data set because my model will not be able to learn from my data set because of this vanishing gradient problem. As I told you, if you will use sigmoid, we will have this problem. The gradient will be this small value. If you will use hyperbolic tangent, it will be much better a little bit because it will be a little bit larger. But if you will use softmax, it would be much, much better, right? Softmax is the best so far. I guess we talk about this already. Is also stochastic gradient descent. When it is a stochastic gradient descent, we will use this formula, right? So it will be just t minus y multiplied by x. We will not have this summation. Okay, this one, stochastic gradient descent. So it will be delta omega, it will be eta multiplied by so it will be eta multiplied by t minus y multiplied by x. If you want to use adaptive learning rate, so just select eta equal bb constant divided by number of iterations multiplied by constant. So in this case, we can start from large learning rate, and when we are close to the optimal point, we will have very small learning rate. So the learning step or the step size will be very small. So in this case, we will start for large step, and when we are close to the this point, we will just lower our speed. So we can reach this optimum point in very smooth way. If you want to use batch gradient, so in this case, you don't need to use t minus y times x, but you need to use the average, right? So you need to take the summation of t minus y multiplied by the input and divide this summation by n. So we will take the average gradient. So instead of using the gradient, we will use the average gradient over n. N will be the batch size. Yes, so it's just, yes, you have this example, in fact, and in this example, we try to adjust this, linear activity, we try to adjust this adaptive linear unit using stochastic gradient descent and the batch gradient descent. So you can see here the difference. When you train your model using a stochastic gradient descent, the error will look noisy, in fact, right? Because we try to adjust for each example. We are not using the mean gradient, but we just try to, in each epoch, we try to apply all my data points. So the error surface will be noisy. It will be noisy like this one. This one, it's a stochastic gradient descent, of course, and it will take too much calculations because in each iteration, in fact, or in each epoch, we apply the whole data sets. So the error surface will be noisy, and it will take too much calculations, right? So it's computationally expensive when we are using a stochastic gradient descent. But when we use batch gradient, what will happen? In fact, it will be very smooth. You see, this curve is very smooth, in fact. So we can converge also at the same time, but it will be much smooth, in fact. It will require more epochs to converge because we update just the weights only one time each epoch if it's batch gradient. So in this batch gradient, in iteration number 1, for example, we will calculate the mini batch gradient, and we will use this batch gradient for adjusting the weights only one time in that epoch, and we will go to the next epoch. So number of calculations, in fact, it will be much less, but it requires more memory. It will be computationally expensive in terms of memory needs, because I need to keep all my data points in my memory, because each time, in each iteration, I need to calculate my mean gradient, and I need to use this mean gradient for adjusting the weights. Maybe in this case, we need more iterations to adjust, right? Maybe if it is a stochastic gradient descent, I can adjust my model in maybe in 50 iterations. In case of batch gradient descent, maybe I will need more iterations, because in fact, we adjust the weights only one time in each epoch. So if your data points is 100 data points, how many times you will adjust in each iteration? For example, if it is batch gradient, it will be only one time. If it is a stochastic gradient descent, it will be 100 times, right? So yes. So we're just finishing. So if you would like to work on some examples, please, you can just try to repeat this example one more time. Try to plot the decision line in 3D, because we did here, I solved this example for iris dataset in 2-dimensional space using, for example, Sibel lens and Betel lens. You can do it in 3-dimensional space. So you can just add one more feature, for example. So you can try to plot this decision line in 3-dimensional space. And also you can make comparison between maybe batch gradient, mini batch gradient, and the stochastic gradient descent. You can try to find maybe running time, memory use, how much memory we need, for example, maybe the accuracy, maybe this computational cost, it will be number of calculations, right? When it is batch gradient, mini batch gradient, and the stochastic gradient, you can try to put your results in a table. So sorry again for today. Today it was a tough day because we had some problems here and the meetings, which must be done, in fact. So sorry for, I apologize for the disturbance today. And we will finish here today, and we will continue next week at the same time. We will start next week from 9. So please, do you have any questions for me today, or? Any questions for today, please?
No, at least from my side.
Okay, so thank you very much. I apologize again for today.
Yeah, no problem.
It's fine.
Thank you very much. And we will meet again next week from 9. Today
Okay.
it's next week it's they call it winter ferian, but for me I'm working. It's is there any one of you will go somewhere with his family or something?
I'm also working, at least. I'm not sure how about
Okay.
the others.
So in this case we will all of us will be attending next Friday, so we will meet again next Friday in the same time, and we will have more time, and I will be better prepared next week. Yeah. Thank you very much.
Yeah.
Thank you.
Thank
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 you.
you.
Have a nice day.
Thank you. The same to you. Nice weekend. See you next week.
See you.
Bye.
Bye.
Bye. Bye. Bye.